In this video, we're going to review different types of chemical reactions. So I'm going to start by overviewing just a number of different types. I'm going to go over 6, and in this class, I really want you to focus on 3 of them. We have combination reactions, which bring 2 or more elements together to form just one product. And so that key of this one is that it has just one chemical formula in its product side of the equation, and that's how you can tell you're looking at a combination reaction. An example of this is bringing together sulfur and oxygen, 2 different molecules that combine into just one, which is sulfur dioxide. Then we have decomposition reactions, where a reactant actually splits up into 2 things. And we have seen an example of this already in nuclear chemistry. So the characteristic of these decomposition reactions is that there's just one chemical formula on the reactant side this time. And looking at a nuclear decay equation, we had just one thing on the left-hand side of our reaction arrow, and then 2 products. So carbon-14 would decompose to nitrogen-14 and a beta particle, which is basically an electron. We then also have single replacement reactions. And this is where we have the same number of reactants and products. So we'll have, so we're looking at single replacement, 2 on each side. So 2 reactants, 2 products, but we switch out kind of a component of their identity. So our hydroxide ion in this example will replace the bromine in methyl bromide, and then that bromine will become an anion separate from the methyl group, and then our methyl will combine with the hydroxide. And so these basically just swap. So these are types of reactions that you might see. The 3 that I would like to focus on in this class are double replacement combustion reactions and redox reactions. So starting with double replacement reactions, this is when we have 2 different ionic compounds that essentially swap cation and anion. And from this, in our products, we usually have one of our products that is forms a solid in water. And so what we have is a precipitate that forms, and that's an insoluble salt, and it basically looks like in my glass of water solution that suddenly out of the blue solid appears, and it collects on the bottom of my beaker. Kind of like, sometimes it looks like a snow globe, sometimes it looks like it gets really cloudy. So in these types of reactions, we see that when we combine different ions that are soluble in water, we combine iodine and lead as 2 solutions where those are soluble ions. And when the lead and the iodine are in the same volume of water, they will form a solid rather than being dissolved in that water. And that forms our precipitate. Because whatever our solid is, that's going to be our precipitate, which I tend to abbreviate PPT. The next type of chemical reaction is a combustion reaction. These happen for anything that contains carbon when it burns. So we often think of campfires for a combustion reaction, but you can think about the combustion reaction that your body does over a number of steps to break down nutrients, food that we've ingested. And so these always have a pattern where you have oxygen as one of your reactants, and then you have carbon dioxide and water as 2 of your products. And that carbon dioxide carbon is forming from the carbon in your starting material, and the hydrogen from your starting material is getting turned into the hydrogen in water. Lastly, we have reduction oxidation reactions, and we abbreviate these by calling them redox reactions because they always go together. And in these reactions, electrons are actually transferred from one compound to another. So there isn't a specific reactant or product that you always see, and there isn't a specific number of reactants or products that you always see. Instead, what you notice, or you try to notice, is a change in the charge of your reactants and products. And so some of these can look rather complicated, and some of them can be really straightforward. Looking at what's kind of in the middle here is iron and oxygen forming rust, which is iron oxide. And I'm not seeing any charges directly on this. So I have to do a little bit of interpreting. When I see an ionic compound, a metal and a nonmetal bonded together, I can think of these as being two different ions that are held together through electrostatic attractions. My iron in this case has a +3 charge. My oxygen has a -2 charge. We reviewed how to do this when we talked about ionic compounds. My iron in my reactant side is just iron metal, and so that means it's a neutral atom. It has a charge of 0. My oxygen is also in its elemental state, so it has a charge of 0. Our nonmetals, when their elements are oftentimes going to have 2 or more of the atoms covalently bonded together, but they'll still have a charge of 0. And so I can see that my iron 0 becomes an iron +3, and that's the change in charge that I'm looking for. And my oxygen becomes an oxygen -2. So that's another change that I'm looking at. So we have a change in the charge of our reactants to products. So now I'll walk through each of these separately. Let's start with double replacement reactions. So our double replacement reactions, we combine a number of ions that are aqueous. And remember, this phase means they're completely dissolved in water. So I wouldn't actually see them. It would be a homogeneous solution. When I bring them together, I know that the combination AB is aqueous and not a solid, and same with CD. So now I compare the other possible combinations of ions, and that would be A, the cation from one combined with D, the cation of another, or the cation or the anion of my first one with the cation of my second one. And that would give me B and C combined or A and D combined. And to find out if either of these would be a solid or if they would continue to be aqueous in solution, I would rely on a solubility table or solubility chart. And a lot of times we summarize these with solubility rules that are general guidelines for determining if a compound would be soluble in water and therefore aqueous, or if they would be insoluble in water and therefore have a solid phase. So for my example here of potassium iodide that we showed before and lead nitrate combining to form this insoluble lead iodide compound and potassium nitrate, once I switched my cation, my potassium cation in this case, for the anion of my other compound, nitrate, I would come and look for a rule that told me if it was soluble or insoluble. And I can find right away on this that under soluble ionic compounds, nitrates, so compounds that have NO3, like this one right here in my products, are always soluble, and there's no exceptions to that. All right, so that'll be aqueous. Now I'll look at my other one, my lead iodide. Coming through here, I don't see lead listed in my general soluble or insoluble compounds, but I do see iodide, and that matches. So iodide compounds are typically soluble, but if I look at my exceptions, I have an exception for lead. which means lead iodide would be insoluble in water. So this would form a solid. And this is the compound that I would expect to precipitate out of solution. In fact, it looks like a yellow cloud forming in an otherwise clear solution when it forms. So I need to swap the ions, then compare my products with my solubility rules. Determine if there is a precipitate. If nothing precipitates, if nothing turns into a solid, then there's no reaction that's really taking place, just mixed some things together. And if a precipitate or a solid does form, then we have a double replacement reaction. Where this gets really interesting, so the solubility rules table that I just showed in the previous slide, perfect. This one right here, you'll have this on exams and quizzes, but there's a different type of solubility chart that you might see in hospitals, or you definitely will see. And it's a compatibility chart of IV solutions. We see IV solutions in health settings, and these oftentimes have ionic compounds dissolved in them. And if we combine two IV solutions that are incompatible in kind of the medical language of it, or undergo a double replacement reaction in the chemistry language of it, we can see precipitates form. And when you combine IVs, you'll see those precipitates form in the actual IV line. And these are 3 examples showing incompatible IV solutions that have been combined and have a precipitate form. Now, looking at this in the IV line, it's like, oh, wow, there's some solid in there. But bear in mind that this reaction is happening as these fluids combine. And so this reaction is happening also inside the patient in their veins, which can actually be extremely disastrous. It can lead to organ failure if you have crystals forming in a patient's bloodstream. And also there's a situation where instead of forming crystals, the therapeutic effectiveness of the drug decreases. And so while administering a certain amount of a drug, the patient is not effectively getting that dosage. And so you see these compatibility charts that look like this in hospital settings that allow nurses to quickly make sure and double check that the solutions that are being combined are in fact compatible. And we can look at one example of something that would be common, or just an ionic compound that's common in a chemistry lab. Like, let's look at sodium bicarbonate. Sodium bicarb is something we use a lot in the lab. It's also something used a lot in medicine. And if we take a look at this, there's several places where there are incompatible IV solutions, and a lot of these are actually for different types of drugs instead. But let's look at one right here. Calcium chloride. So here it's saying that sodium bicarbonate and calcium chloride are actually, bicarbonate, there's an H. These are incompatible. And it's because they actually form a precipitate. In this case, when you combine these, we would say, all right, let's take the cation from one and the anion from the other. And then we'll take the anion from one and the cation from the other, and we'll combine them. When we do this, we would get, we'll need 2 of these. 2 sodium chloride, because remember my sodium will be +1. My chlorines will each be -1. So they combine in a 1-to-1 ratio. And sodium chloride is going to be aqueous. We can double check that with our solubility rules here. And if we look at chlorides, they're all soluble except for silver, mercury, and lead. So that means if I combine it with NaCl, this will be soluble. And then our other one that forms, oops, too far, is going to be our calcium and our HCO3. We'll have two of those. So our calcium has a +2 charge, and our HCO3 has a -1 charge. Now, if we take a look at the chart, we probably won't find it on this one as we have kind of a simplified chart here. And in fact, we don't have the HCO3, the bicarbonate ion, anywhere on here. But our bicarbonate ion is going to be in equilibrium with its carbonate form, which is -2. And this is something that is explained by, and we'll go into detail when we talk about acid-base chemistry at the end of the quarter. But we do see that on our solubility chart, and these are typically insoluble unless they're paired with ammonium or an alkali metal cation. So that means we would expect our calcium carbonate to be insoluble. So we will assume that this then becomes calcium carbonate through an acid-base reaction, and that it will be soluble. And so this would be the precipitate we would see in a IV line. Now let's move on to combustion reactions. Combustion reactions always have this same format. You have some combination of carbon and hydrogen in different ratios. Like some examples would be methane, CH4, or propane, C3H8. And they're always combined with oxygen as a reactant. So that is what I look for to determine if something is actually a combustion reaction. It react with oxygen as a reactant. And they'll typically have carbon dioxide then as a product and water. Sometimes this carbon dioxide, if there's limited amounts of oxygen, it'll be carbon monoxide or carbon soot. But we'll always have this water along as well. And it also produces lots of heat as well. I mean, a campfire is a combustion reaction, and we sit around it for heat. And so we'll always produce heat, we'll always produce water, and usually carbon dioxide. And so that's how you can identify a combustion reaction, by just looking at a list of different types of combustion or different types of chemical reactions. The last type of reaction I'd like to speak to is oxidation and reduction reactions, or redox reactions. These are the reactions that have the charge is changing on our products. And what's happening when a charge changes, and in our previous example, we saw iron with no charge becoming an iron with a +3 charge. When we looked at our iron combining with oxygen to form iron oxide. So this change in charge really is representing a change in the number of electrons that this atom has, because its protons and neutrons are defining it, or its protons are, and we're not being told that there's a change in mass number. And so to balance out this charge, this iron here on the reactant side is either gaining or losing electrons in these reactions. Now it forms a plus charge, which means, and this is strange because it's gained, it's gotten a larger plus number, so +3 versus 0 is a bigger number, but it means that it's lost electrons. So it has 3 electrons that have separated from the iron and are now able to be donated to another atom or molecule. And if we think about this, the charge in the iron is +3, and we're adding the charge of the electrons, which is -3, and that equals 0. We need our charge to balance on either side of our reaction arrow. And so we have 0 total charge on either side. On my product side, it's just been separated. And so when we lose electrons, we define that as oxidation. And you'll sometimes see oxidation of the iron being represented as instead that iron is a reducing agent. I find that language pretty confusing. So I'll always stick to oxidation or reduction of something instead. So in this case, that example I gave, because there is there's a loss of electrons, the iron is oxidized. And these reactions are always coupled together. There isn't just an oxidation reaction or just a reduction reaction. So when these 3 electrons leave the iron, they go somewhere specific. In our previous example, this was actually to the oxygen. The oxygen that we had went from O2, which had a charge of 0, to oxygen -2. There were 2 of them involved too. And so what's happened here is the product has more negative charge than the reactants do. So it gained electrons. So my reactant plus electrons gave me my product. So this gaining of electrons is what we refer to as reduction. So this O2 is reduced, where iron is oxidized. And what's happening here is we are transferring electrons from an element to another. And we're really creating ions that can form ionic bonds. Here's another example of zinc and copper. And in this case, we can see that the zinc has a 0 charge because it's just a metal on its own. And it's forming zinc +2. So because it's becoming more positive, it means it's losing electrons. The zinc has then been oxidized. Now the copper has a +2 charge in our reactants, and it becomes just copper metal with a 0 charge. So it's really going to gain 2 electrons to get to that neutral copper atom. And so because it's gaining electrons, it is being reduced. And we can write out half reactions that are really specific about this. So this is how we would combine things in a chemical reaction up here. If we wanted to really show where these electrons were going, we could write 2 half reactions to represent a redox reaction. You have zinc forming zinc +2 and the 2 electrons that are lost. And then we can show copper forming copper +2 ion forming copper metal, and it needs to gain 2 electrons, so they go on the reactant side. You can see that if we combine these two, our electrons will actually cancel when we combine these 2 reactions, and so their sum will be what we already have written for the overall reaction. But this does help highlight that zinc is losing electrons and copper is gaining electrons. And here are those oxidation reduction half reactions written out in a neater format. So here are 2 examples I'll walk through. So let's try to write out these oxidation reduction half reactions and identify what's being oxidized and reduced. So when I see a reaction like this and I'm asked to do this type of problem, the first thing I do is I try to assess the charge on everything that I see. So when I have sodium alone and it's solid, I know that this is just an element. So it's got a charge of 0. Same with Cl2, that's just elemental chlorine, so it also has a charge of 0. When I see NaCl, I know I'm looking at an ionic compound because it's a combination of a metal and a nonmetal. So this is really sodium +1 and chlorine -1. So my sodium metal is becoming sodium +1, and my chlorine gas is becoming 2Cl-1s. Actually, I have 2 sodiums, so I'll put coefficients in front of those to keep this balanced. So in one case, I'm losing electrons, and one I'm gaining them. And so my chlorine, which is also at 0, to be able to form a -1 charge, it needs to gain an electron from somewhere. And for my sodium metal to have a positive charge, it needs to lose an electron. So I can write that electron as a product. And so my sodium is losing electrons, therefore it is oxidized. And my chlorine is gaining electrons, therefore it is reduced. Let's try that again. So if you'd like to try this second one first on your own, I would hit pause, and I will continue with the solution. So in this case, we have magnesium metal again. So this has a charge of 0. Oxygen gas, or O2, is the elemental form of oxygen, so it has a charge of 0. And then I have MgO. I've got a metal and a nonmetal. So to me, I know that that's an ionic compound. I know that my magnesium's in my second column, so it tends to form a +2 charge. And my oxygen has 6 valence electrons, so it'll form a -2 charge. So I can look at my magnesium. My 2 magnesium metals with 0 charge are becoming 2 magnesium +2 ions. And my oxygen, which was O2 gas, which is an element, so a charge of 0, is becoming 2 O oxygens with a -2 charge. So here my +2 charge on my manganese means I've lost 2 electrons in this process. So I'll have 2 electrons in my product. The -2 charge on the product of my oxygen tells me I gained electrons from 0. So I need to bring 2 electrons from somewhere to this oxygen, this O2, to form my oxides. So this loss of electrons is manganese being oxidized, and gaining electrons means that my oxygen is reduced.